and move on to the next talk by Phillip Kim. Phillip, are you ready?
Yep.
And apologies for the delay.
It's already good to have the more discussions than no discussions.
Agreed.
Yeah. Okay, well, thank you very much for inviting for this workshop and sharing some of the development in the probably traditionally non-conventional material platform to realize Majorana or beyond the non-abelian quartz particle. But I think I'm happy to report some of the progress we are making. The work that I'm going to report is combining the superconductivity and the fractional quantum effect in the graphene as a material platform. We have the collaborations within the group as well as the intergroup that we have the great support from Amir Kubi's group, and especially in the theory that Hassan Shaporian working with Ashvin Vishwanath make the kind of significant contributions on the theory side. The experiments basically carried out by the two postdocs, On the Go and the Yuval Ronen. They are equal contributor of this work, and most of the recent report is posted into archive a few months ago. Okay, so throughout these 2 days workshop and the last sections, that we've been just kind of examining through the many different platforms one can realize the topologically protected qubits. And traditionally, this starting from that basically the even denominator fractional quantum states and using the more real state to realize non-abelian quartz particles into the system. But increasingly that the interest seems to have moved on in the past decades, some sort of combination of the superconductor with the various different material platform, like the topological insulator, 1D semiconducting wires, or the ferromagnetic atomic chains. And the goal that the community is setting up is, can we actually realize reliable non-abelian quartz particles and based on this topological superconductivity by approximatizing some of these topological systems. While that we've been seeing a lot of the progress, as we heard about in this the workshop, there are yet another material platform we can also think about moving forward in a similar way. And that's basically this so-called two-dimensional materials or Van der Waals materials. We're coming with many different platforms. Graphene, boron nitride, metal dichalcogenide, even the cuprate, and more of the exotic system. There are many 2D materials available with the various different flavor, including topological insulator, right? Moreover, the possibility of stacking these materials up, that there is a possibility we can create some of the functional interfaces that we can rely on as a material platform to realize that the topological superconductivity. Today, what I'm going to just discuss is just one kind of material, so just the graphene. However, even for the graphene, the recent progress or the community-wide progress made the graphene becomes extremely good, high quality 2D materials at this point. By combining with the boron nitride or all the Van der Waals stacks, including all the gates and all the structures, now the mobility you can achieve in the graphene is extremely high, something like easily millions or tens of millions. It's basically limited by the size of the sample one can get. And furthermore, because the graphene is a semi-metal or the zero-gap semiconductor, making contact is reasonably easy. So making the various contact, including the superconducting contact, is reasonably easier than a semiconducting platform. And this will immediately give us some of the advantage to using the graphene as one interesting platform. And quite recently, I think it's been demonstrated, this is a result from the Corey Dean's group at the Cornell, the Columbia, demonstrating that within the lab chip magnetic field, they can demonstrate all this fractional quantum effect down to even denominator states realizing the bilayer graphene. And this basically gives us some hope that maybe we can just use the graphene as a material platform to combine with some things that getting into creating topologically protected qubits. Now, and the other part is that a lot of the gates and the contact control is also possible. Now, the state of the graphene fabrications now allows us to make the graphene rather complicated devices. So this is a good example that one can realize this quantum interferometer, the Fabry-Perot type of quantum interferometer. At least we started getting this interference in the integers and pushing to these fractions and hopefully bring it to the more of this the even denominator states and bring this graphene as an important material platform, also realizing this quantum-based the topological qubits. Now, today, I'm not going to dwell on this one, but particular topic I'm going to discuss today is basically using the graphene as a material platform to realize combining the superconductivity and fractional quantum Hall effect, try to bring this as the first step toward the topologically protected qubits idea. Right. The idea about combining the superconductivity and quantum Hall effect has been around. One of these first idea came around the Xu Chengzhang's work that basically proposed that combining superconductor with a quantum Hall effect or quantum anomalous Hall effect, one can create this topological superconductivity, approximatize the topological superconductivity. For example, in the vortices on the this type of the combined system should contain the Majorana zero mode in there, and manipulating that, one can just realize some of the topological superconductivity with the Majorana zero mode at the nucleated defects. In fact, this idea that around that first proposed in 2010 quickly just push even further. What if now, instead of the combining superconductor with the integer quantum Hall effect, what if we just combine that superconductor with the fractional quantum Hall effect? Within a few years, there are several groups, many of the authors, in fact, in these conferences, collectively come up with the idea that indeed, if you combine that superconductivity with the fractional quantum Hall effect, you can realize it, generalize the Majorana mode or the non-abelian anyons called the parafermions with the multiple ground state is possible, right? So it is in some sense generalized Majorana mode. And this parafermions platform, if they do exist, it can be used as just the more close to universal quantum computations. I think that's kind of one of the really excitement that maybe just pushing this idea to combining the superconductivity with the fractional quantum Hall effect, one can go even further beyond this the Majorana physics that we are looking for. While the theory proposal is out there, also the idea of the combining the superconductor with the quantum Hall system has been around almost 2 or 3 decades, quite a long time. And in particular, that try to combine with the superconductivity of fractional quantum Hall effect, you need to come up with the idea that how to make the good contact with the superconductor, which actually has a very high IC2, such that the superconductivity can survive within reasonable magnetic field that one can set up to realize the fractional quantum Hall effect. One of the notable example is here. It was done by the Leonid Rockinson group at Purdue in 2014. They just used the gallium arsenide, the 2DEC, combining with the niobium superconductor, where the fractional quantum Hall effect sets in the few Tesla, which is well below that HEC2 of the niobium, and they demonstrate at least that they can use a superconducting contact to measure this fractional quantum Hall effect. While that this is give us the intriguing result, as you shown here, making this reliable contact with the niobium with this the semiconductor was not too easy. Part of the reason is, well, that you have to really fight with the Schottky barriers, especially coming from this refractory the metal like the niobium, and that's been kind of struggle and making reliable contact with the semiconducting the material has been some of this big technical challenges. Of course, there, as I said, graphene has advantage because there's no gap in principle, the semiconductor gap. So therefore, you can make this a decent contact with many different material, including the niobium or the molybdenum, and those kind of type 2 material with reasonably high HEC2. And here's another example, the one example that Finkelstein's group actually demonstrated with many other groups, also similar result. Making the good contact with, in this particular case, molybdenum with graphene as a channel, and they apply the magnetic field, the graphene get into the quantum Hall region, and then yet the superconductivity in the molybdenum is survived. So in this particular example, they demonstrated that coexistence of the quantum Hall appears a plateau in the two terminal conductance. At the same time, they demonstrated that there's a Josephson effect appears between these two superconductors through these quantum Hall channels in between. However, this is not precisely coexistence in a sense. By definition, having Josephson effect means you have you need kind of the zero resistance. In quantum Hall in two-terminal, you have always kind of quantum Hall plateau. So what they see is in the middle of the quantum Hall plateau, sometimes it's the resistance dip into zero to show this the Josephson effect in the middle of the plateau. So there is an alternation of the quantum Hall physics and the Josephson effect in there, but it's not necessarily kind of truly coexistence cases in this particular case. But this brings us some of the interesting directions we can just look for. Instead of using the Josephson effect, can we actually just really probe the coexistence between superconductivity or proximatized quantum Hall edges together with prove the coexistence superconductivity and quantum Hall physics by just showing the proximatized quantum Hall edges. One of the idea here is using Josephson junction. In other words, just kind of use Andreev reflections. Well, we know that in Andreev reflections, when carriers coming from the normal metal to the superconducting interface, you can inject a Cooper pair into the superconductors by having this the retro traveling the holes back from the interfaces, right? So idea is instead of using the normal metal, can I just deliver the current through the quantum edge state to the superconductor and just can detect this the holes coming out from this Andreev reflection process. These Andreev reflections usually appears as an enhancement of the interfacial conductance and the zero magnetic field. Basically, just looking at the how the conductance got enhanced will tells us that how perfect is the interface between the superconductor and the normal metal. And this enhancement can go up to the 100% because all the electron gets in, reflect by the hole. Basically, I have 100% Andreev reflections, and then I expect to see the 100% enhancement. Of course, the interface is not perfect, and you start to kind of develop some barriers, and whatever barrier it is, and then if the Andreev process start to reduce, then of course this conductance enhancement will reduce. Eventually, if this is complete tunneling of the free carriers, then you expect to see that this tunneling conductance type of the measurement or complete suppression of the conductors in between. So idea is the first, can we actually build up the superconductor and the graphene channel and demonstrate whether enough the Andreev reflection can be measured under the presence of the magnetic field. So here's an example that here that we use a graphene, and then as the superconductor, we particularly use this the combination of niobium and niobium nitride. Use titanium as sticking layer, and this the combination provides us extremely efficient contact to the graphene through the tie layer, but big presence of the niobium nitride give us quite high HEC2. In fact, our estimation of HEC2 in this device is well beyond the 20 Tesla, somewhere in the 25 Tesla to 30 Tesla. This is high enough magnetic field that one can, in principle, realize the fully developed the fractional quantum effect in the graphene channel with the decent graphene devices. Indeed, when we measure the Andreev reflection in this type of device with this the combination, we see that in the zero magnetic field, about 50% of this the conductance enhancement, indicating that indeed we can make the fairly good contact onto this device. And with the magnetic field, of course, with various regions, the vortex formations or various regions, this conductance enhancement actually reduced. In other words, the Andreev reflections efficiency reduced, but still up to the 12 Tesla, we get about 10% of enhancement. So it's, I think, it's still reasonably effective, such that we can realize the experiments that by combining that quantum Hall edges with the superconductor. So what you can observe. So very similar device, but I'm just using again Gladdenkerstein's recent experiments showing that how the Andreev reflections work when the graphene channels undergo to the quantum Hall, and then you have the superconductor contact that grounded such that there's Andreev reflections happening through this the edge states passing through this quantum Hall, and one can detect that information, measuring basically downflow of the quantum edge state chemical potentials, right? So naively, what you expect to see that is when the electrons start to bump on the superconductor, it will just kind of go through this Andreev process. Each Andreev reflection process converts electron to the hole. And again, downstream hole will process in the same direction, and that hole will just convert into the electrons and holes and that, right? So you can see that there is a successive transform the electron and holes when this quantum energy states just traveling across the superconductor, where you keep just getting into superconductors to create this group of pairs, right? And this process eventually, if the superconductor is long enough, then we'll mix up the electron holes, and then in the downstream, basically some of the mixture between the electron hole and detail depends on the length and then all the kind of geometries and scattering process of these cases. So, but in the end of the day, in the downstream of the quantum edges, you will see that it's just basically mixtures of the electrons hole, which actually can sensitively tuned by the gate voltage and magnetic field. Indeed, what the Finkelstein group actually observed is, if you just carefully monitor the downstream, the quantum or the chemical potentials, you see that there's a lot of defined fluctuations of the chemical potential of the downstream of the quantum edges, more like the symmetric C-shape from the zero, the positive and negative is rapidly processing. Part of the reason is basically as you change the gate voltage or magnetic field, that whether final electrons comes out, hole comes out is depends on the details of the system, right? So while you see that there is the Andreev edge process or Andreev states, the edge state forms along the superconductor, this may not be too useful for now, right? Although there's an interesting effect we can see as a fluctuations. However, this actually gives us kind of another idea. Maybe we can proceed a slightly different way and give some differences. So imagine that I have this quantum Or states, quantum Or the samples, and with the 4 normal contact is they connected. So typical way that I can measure this multi-terminal measurement is I just bias the one of the contact and ground one of the contact, and measure the voltage in the upstream and downstream. And basically this upstream voltage and downstream voltage, by the way, should be 0, right? And I will get this whole resistance, Rxy, by just reading of this 2 voltage difference and divide by the current, right? So that's kind of typical quantum physics. What if now I just replace this contact, especially this ground contact, with the superconductor? Now, when I just replace with superconductor, as I just briefly explained, when electron comes in, electron will replace to the hole and electron hole, and you start to see that this Andreev edge state is happening. As I mentioned, if the superconductor is this length of the contact is long, eventually you will just mix up all the electron holes. In downstream, you get more like the mixtures, right? Although they are fluctuating, but if you just average over, more of you get the 0. So as if I just measure the whole voltages, nothing changes, suppose changes when the system get into the quantum Or. When this contact is replaced by the superconductor, right? Every time that the Andreev process is happening, then when you have this the electron group of pair or whole group of pairs that getting into this superconductors, right? What if now though, if I just make this superconductor thin, such that across this superconductor, basically instead of you get this the Cooper pair forms by just combining Andreev process on one side. What if that superconductor itself is thin enough to compare with the superconductor coherence length, such that hole is not grabbed from the same side of the contact, but hole can be grabbed from the other side of the contact? And this is what we call the cross-Andreev reflection. If that is happening, and if that is dominant process, what we expect to see is the electron comes in, will directly convert to the hole, and I expect to see only in the downstream, just to read the downstream negative hole voltages on, right? And so basically that's the idea, that instead of fluctuation, I should be able to see the solid negative signal in the downstream of this quantum edges. So that's basically the idea that we are going to use, and just use these cross-Andreev reflections. We want to kind of show that indeed this quantum edges, incoming quantum edges, are proximatized by the superconductors, right? Indeed, this experiment actually worked it out a few years ago already. Here that is a graphene and niobium nitride electrode, except now the niobium nitride electrode is so thin, something like the order of 100 nanometers or even less, right? and measuring the bias, the upper side of the quantum lattice and ground with the superconductor, and we monitor the downstream of the chemical potentials, and that normalize the chemical potential with the current, and that is what we call the cross-Andreev reflections resistance. And then indeed, whenever we see that the quantum hole is well developed, like the 6, 2, and 1, and single layer, the quantum hole effects in graphene, we do see that indeed the downstream of this chemical potentials dip into the negative side. You see that signal is not necessarily big. Something even in equal 1, we get about 50 ohmish of the resistance, which we're supposed to get about 25 kilo ohm. It's very small. It's about few percent, about 1% or few percent of the signal. But clearly that negative signal is well beyond that our detection limits, so indicating that indeed we can make the cross-Andreev reflection across this thin superconductor. Now, one of the idea that just viewing this cross-Andreev reflection is using the concepts of the Majorana physics or semiconducting nanowire type of the idea. Now, when we make the contact, we basically remove the graphene underneath and backfill with these superconductors, right? So for a moment, if there is no superconductor, basically quantum edge state will just follow through the trench we created like this. Now, presence of superconductor is basically the coupling these two counter-propagating in terms of spatial direction of the quantum edges through the superconductor. Basically, this has a very similar flavor that one can create this the Majorana edge states, Majorana states at zero mode onto this quantum the semiconducting wires in very similar formats. So one can just view this type of this cross-Andreev reflections combined with a very thin superconducting contact as a kind of analog of this the forming Majorana zero mode and semiconducting nanowires with the the proximitized superconductivities, right? How do I know that this is really the case? One way you can test that out is basically varying this width of the superconductor, right? Because we know that the superconductor need to be thinner than the superconductor coherence length to provide the cross-Andreev reflections. If indeed we make the superconductor thicker and thicker, we expect to see that the signal will quickly go away. Indeed, if we just varying this superconducting the contact, the width from say below 100 nanometer through this something like a few hundred nanometer, you can see that those kind of the negative signal we are getting exponentially decays with this width of the superconductor, and that the parameter we can extract out of this is basically the superconductor coherence length, which is about kind of 50 nanometer-ish of the length scale, which more or less agrees with what we expect to see that in niobium nitride, the superconductor. So at least we know that the basic idea of using these cross-Andreev reflections to just probe the proximitized quantum edges seems to work. Now, the next level here is, can we actually just push this into now, not only integer quantum hole, but fractional quantum hole effect? For that, we need kind of just bring up, boost up our device verification even further. What we need is an extremely high quality graphene channel to realize this type of experiments. So we have to bring up this the graphene encapsulated boron nitride, and more critically that we have to put this top and bottom graphite gate, provide completely van der Waals stacks and without any impurities, and that fabricate the devices out of it. It's challenging. It's doable. Here's a device, the overall images, and this is normal. The gold color is a normal contact made of the Thai gold, and here is basically this the cyan color is the narrow niobium nitride contact. Especially essential part is end of this niobium nitride contact. Width is about 100 nanometer, even less, right? And then as I said, that graphene underneath of this contact is removed first and backfilled with the niobium nitride. So you can think about this as a trench of the graphene channels backfilled with this superconductor. And another important aspect is we have to carefully etch away this top graphite, the gate such that in fact that there is a region of around this superconducting region where we can separately control this the density, which actually plays an important role in the last topic I want to kind of touch upon. We made kind of say many devices. We measure about 5 devices, and that more like the result is agrees. There are some statistical variations. Of course, we are just showing the best data, but more like the stories agrees upon that many different devices that I'm going to show you. Right, so measurement scheme is following. As I said, we will just inject the current from the upstream. So there's current to kind of bring it down. And superconductor is always grounded, and such that the current is always kind of drained through the superconductor. And in the downstream, basically we can monitor the chemical potentials to see the downstream chemical potentials. At the same time, we can measure the RxX and RxY using this voltage probe and carefully delineate this contact, the equilibration problems throughout this. So what do we expect? Basically, when we measure the quantum Hall effect with the superconductor as a drain contact, basically quantum Hall effect should not be affected. RxX, whatever contact you are making, is always quantized. Goes to 0, right? RxY should be always quantized because it's topological property of the quantum Hall channels, right? Interesting part is this cross-Andreev reflections, downstream the chemical potentials normalized by the current is arranged between, if the cross-Andreev reflection is happening, it should be negative. There is no cross-Andreev reflection, it should be 0 because basically you are seeing that the carrier is coming from the ground, and in normal carrier, basically I expect it to be 0. So it can be 0 to some negative number. It is bound by half of the RxY if everything is completely cross-Andreev reflected. So we know that that's the range of this R-car, and we can see that strengths of the cross-Andreev reflections by simply measuring this R-car, right? In fact, you can just work it out, a little bit of math, and then you can convert this R-car into this probability of the cross-Andreev reflection per channel. And that's what we call the P-car, which is basically obtained for divided by R-car divided by R-car plus RxY. But typically, as I already briefly mentioned, R-car supposed to be as big as RxY divided by 2, but typically this is a much smaller value. So R-car is smaller than RxY, which means that usually the probability of the cross-Andreev reflection is obtained by taking the R-car divided by what is R-car? R-car divided by RxY. Sorry, there's a typo here. So that's kind of the how you want to kind of look at the data. So let's look at the data now. With this much higher quality sample than what we made 4 years ago, we can do the following experiment. Already at 1.8 Kelvin with a magnetic field up to the 14 Tesla, clearly that this R-car, I'm showing the R-car in terms of the color, negative signal is something the bluish, right? You can see that, okay, RxY showing that this, the typical band-like behavior, then you are seeing that all this quantum Hall Venn diagram, but R-car shows many blue stripes, which means that the car process is quite strong. But more exciting part is that rather than integers, you see that a lot of the fraction car process already started to show up, right? So this is very encouraging. With this device, already we see that many of this fractional quantum effect do appears as a negative cause signals into the signal. A little bit of cross sections at the high magnetic field, 14 Tesla, you see that the RxY shows nice plateau correspond to this all the quantum Hall sequences, including 1 and 2, but more importantly, these fractions. And fractions, and as I just mentioned here, shows a large negative car process value. So, which actually indicating that indeed car is very robust into the fractional quantum Hall states. Now, to make sure that often that this type of the experiments to just bring it up, experimentalists and even theorists ask that, are you sure that this negative is not an experimental artifact? So one thing that we can just do that is it's the same measurement. We simply increase the temperature, especially go beyond the superconducting transition temperature, right? And superconductor becomes a normal contact. And then how this car signal process, I think that is one of the important criteria and we should kind of show. Indeed, this niobium nitride TC is around 8 Kelvin. When you just heat up the system beyond 8 Kelvin, all the negative signals completely go away and completely turn into positive. And that it becomes positive because the car measurement is kind of three-terminal measurement. So inherently include some part, especially superconductor, the part of this contact resistance. And that's kind of naturally expected. But this actually show that indeed the car signal we are measuring is rather the intrinsic effect we are seeing that related with the superconductivity, right? So before I just hit back to the fractional quantum Mode effect, let me just kind of briefly discuss about the integer quantum Mode effect already, which are also already quite interesting. So let's say that if you parked around the 4 Tesla, the fractional quantum Mode effect fully developed, we already see that the 1, 2, 3, 4, 5, and those kind of the RXY shows up here. At the same time, car actually shows up very robustly in the negative values, right? 1, 2, 3, 4, and you see that whenever there's quantum Mode plateau appears, then you get the negative R car value. And you see that car actually increases as you go to the lower filling fractions. And we scratched our head, why actually it's increasing? But we found this interesting that if I just normalize our car with RXY, basically they are more like the same values, right? At this point, you start to remember that indeed, that I mentioned that probability of the car per the quantum Mode channel is proportional to the R car divided by RXY. This means that regardless of this, how many edge states I'm impinging onto the system, per edge state, car process is exactly the same. You equal 1, 2, 3, 4, right? And this actually is a very robust. We just measured many different integer quantum Mode effect between just magnetic 2 to 4 Tesla. As long as this quantum Mode state sets in all integers, including the so-called the symmetry broken quantum Mode edge states, as long as the integers, we get basically very robustly that all this car probability is the same. I think this is rather intriguing. Why is that? Because some of the edge state is far away from the superconductor. So naively, we expect to see that will make the superconductivity, the proximity effect weaker. But nevertheless, car probability is the same. And it turns out that this is basically expected. In a sense, it actually support, indirect support of the topological superconductivity we are creating in the system. So theoretically, if you just try to understand this one, basically you just solve this BDG equations, including the superconductor as a thin wire, the 2 quantum Mode edge states, the up and down, the counter propagate the opposite directions running down in the system, and you just basically approximatize these 2 quantum Mode edges, right? It turns out it is very important that we have to include, especially when nu equal 1 type of things, quantum edge state where spin is polarized, including that the spin-orbit coupling inside of superconductor is very important because niobium is a heavy metal, and we expect to see that, there's a reasonably strong spin-orbit coupling, and that is very important because without that, there is no way that I can make the decoupling between the 2 spin polarized edge state in the nu equal 1, right? Basically, I need to kind of form the singlet, the pairing. Therefore, that I have to really remove the spin indices or make the spin is not a good quantum number anymore by just including this spin-orbit coupling. Now, if you just include this reasonable strength of the spin-orbit coupling, it turns out that then it opens up the 2 independent Andreev states basically couple each other and open up the gap, and this induced gap is kind of directly related with the size of the spin-orbit coupling. So that's as well as the superconductor. So that is kind of interesting part. And important part is it opens up the gap, and this is basically a topological gap in a sense that ensure that there is a 0 mode inside of in the mode, which actually mediate this kind of the Cross-Andreev process. Because of that, in a sense, every time I just add up this quantum edge state, basically I'm adding up this another copies of this type of the topological gaps with the 0 mode in there. In the simple view, therefore, that regardless of the details of the size of this gap opening, basically as soon as the gap opens up and it's resolvable, I expect to see that basically this very similar car process is happening, and that is what we are seeing experimentally, very robust car probability across the system. why the Car probability is so small, about a few percent, about 1% or 0.5% in particular case. It turns out as soon as you just can include some of the barrier like the term, especially in this particular case, co-tunneling of the carrier is spoiling this process. You quickly start to reduce this Car probability, and typically the Z number we just include there is something like about 0.5-ish. Then you get about kind of few percent of the Cross-Andreev process, which is happening here. Right. Now, with this, let's kind of move on to discuss about what is happening in the fractions. In the fraction, basically, as I said, there's a robust fractions happening. In fact, fractional Car. Yes. Yeah.
Sorry to interrupt. How many minutes more do you need? Should wrap up in about 5 minutes, I think.
All right. 5 minutes probably enough, I guess. Hopefully.
Great. Sorry for the interruption.
Yeah, so that's okay. I think, yeah. Let's see that. Let's hit this nutshell. So basically fractional quantum effect, the Car is even stronger, right? And even if we just kind of convert it into the P Car, that it's generally stronger than what is a P Car, the probability that you get in the integers. So it is very robust, and it is even robust when you get into the sum of this fraction, especially fractions less than half, so include 1/3 and 2/5, that there is tendency that fractional Car is even stronger than what is seen in the integer. So it actually brings us kind of some of the wonder why the fractional Car process is even stronger, and especially stronger at the lower temperature. And there's this kind of some of the scenario that we can think about. What actually makes this process the fractional Car? One way, that naive way we can think about is basically I have the edge state of the fractional quantum state that comes in with the say 1/3 state, 1/3 of electron charges. The way that I can just kind of put this Car process is I will just collect all these 1/3 charges to make the 1 charges, right? And then I can form this basically regular Cross-Andreev process to form the group of pairs, and then charge 2 Andreev pairs, and then make this hole on the other side, and this hole will downstream should break down again to the 1/3 of the whole charges. And that's kind of one way we can think about to making this process. The other more drastic idea is instead of that bunching this 1/3 charges to make the full charges to make this 2E Andreev process, maybe you can conceivably think about this getting this 2E star of this Andreev pair or anion Andreev pairs to make the process can happen. In this particular case, I don't necessarily need the bunching. In fact, the theoretical argument tells us that in the upper cases, charge 2E Andreev pairs, since you need a bunching process, it actually costs energies, which means that as you go to the lower temperature, it tends to be suppressed, while that the charge 2E star of the Andreev process, there is no bunching is needed. If this is indeed the ground state kind of close the ground state properties, in fact, you expect to see that stronger the process happening at the lower temperature. So temperature dependence may actually tells us these distinctions. Indeed, when we just look at the temperature dependence of the Car process with the temperatures with the Car, we found that indeed the process for especially 1/3 and the fractions and that 2/5 is stronger as you go to the lower temperature, strongly support that the idea of this charge 2E Andreev process. In other words, it indirectly proves that the existence of parafermionic states in this type of the system. I know that Jerry is kind of now pushing me, so let me not go into the details, but all of these things also can be carefully discussed again by changing the chemical potential near this contact area. And just kind of, we can just take the look. Indeed, 1/3 and the 2/5 actually goes a rather different process with all other integers or even all other fractions in the higher filling fractions. Also strongly indicating that indeed we are seeing the fractional Car process is rather different from this integer Car process. And that's basically indirectly support the idea of the formation of the parafermion, in my opinion. Okay, so where we are going. So we have to really just show the next step, indeed the existence of parafermion. There are many different ways. Well, graphene, one can also make this the Josephson junction. Already some of the efforts we are just providing, or we can just follow through the semiconductor wire type of experiment. We can try to do tunneling experiment at the end of the superconducting wires where the parafermion sits in, or we can try to even just directly measure this the fractional car process, basically measuring this the short noise type of the measurement. So that's kind of something that we are thinking about. Thank you.
Thank you. Very nice. I would open the floor to questions. I just wanted to express a wish to actually, yes, ask you a question about the power fermion Cross-Andreev reflection. So maybe I'll start out by asking it. So you were suggesting that there's a possibility of 1/3 coming from the left, and was it minus 1/3 coming from the right?
Yeah.
Or is that right? And that will give you. So I find it a little confusing. So let me try to clarify. So the Cross-Andreev reflection, an electron comes from the left, the electron comes from the right, comes out as a Cooper pair.
Yes.
But here it's right.
So let me see whether I can do it right. Right.
But
so
that's neutral.
Yeah, whatever things. Let me just see that. I think I have that even better. I think. Let me see that one. Okay.
Yes. Yeah. Exactly.
This guy is a little bit better diagram. So let me just show you. Rather than so let's see that. I think, you can see here, right? So the process that we are proposing is indeed. This is likely than this one, right? So we have the 1/3 coming down here in the downstream. Basically, it's 1/3 of the whole, right?
Yep. And
then we form this the 1/3 charges of the Andreev process. Basically, that is the proposal.
And then you have like a 2/3 E coming out as a Laughlin-Cooper pair.
Not sure whether I can call this a 2/3 of Laughlin Cooper pairs. I want to say that this is basically Andreev pair states of the 1/3 charge. I think that's a kind of yeah. But I think maybe it's something that you can just put in a different way, right? Yeah.
But you could also have the 1/3 coming from one side and 5/3 coming from the other side.
I think that's in principle that's also kind of possible. I think there is no restrictions except that. In the end of the day, I'm having the faraway superconductor. Anyway, I should say that this is just the 1/3 of the charges, the quantum edges, right? So not sure whether I can just change even that, especially far away from the superconductor. So I don't know whether I have the other choices than this one. But this is a kind of good point. I think at this point, this is just a naive proposal, right? And then the experimental evidence I can present here is only the temperature dependence of the car process, other than all other the outlook type of experiments. So any of the things that I just draw cartoon, you have to just take as a grain of the salt.
This is cool. Brings back good memories from the theory work. Anyway, let's take one more question before continuing, or let's see. So maybe two more. So I see a question from Kirilo Snishko. Go ahead.
Hi. I wanted to ask this question. You talked a bit about the spin-orbit coupling, that you need to make the two edges talk to each other. And in Moti Heiblum's group, there is this strategy to make two quantum wells in gallium arsenide and bring two edges of opposite spins close to each other. I wonder whether this is possible with two layers of graphene, and I have a suspicion that even bilayer graphene would work for that purpose.
Yeah, that's right. Good point. I think the original theory proposal is indeed that comes with. I think Jason's the proposals comes with the in fact put the gate on the half and just kind of try to convert into the opposite side such that you don't have to bring this spin-orbit coupling arguments, but basically you flip the spins on the other side. But as you just kind of rightly mentioned, graphene, those kind of geometry can be done rather than putting this lateral gate. I think there is one. Yeah, here we go. Yeah, something like this is what you're saying, right? So indeed, kind of, we are just trying to get this not onto the trench type of the geometries, but you can also put the double layers. And if you just gate in top and bottom layer, and then you can make this whole Landau level, electron Landau level, and the spin is opposite directions, right? And then still you have the nu equal 1, for example, or the fractions. And then you don't have to rely on the spin-over coupling anymore. I think this is kind of interesting idea. We are just trying to also pushing this experimental this side. We don't have yet the convincing data, but certainly that is one of the conceivable experimental idea we can implement.
I see. I'm excited to see the results.
Let's go on with a few quick questions. Alexander Stasiowski.
You are muted, Alexander. Yeah.
Oh, thank you. So I wanted to ask you, if I remember correctly, this old proposals of Schusch and Zhang et al. When you put a superconductor on top of integer hole, so let me just restrict myself to integer hole. So there was always this picture in which the edge mode, which is Dirac mode, would split into two Majorana edge modes, and one would go around and one would go just where original edge was. And in your case, it looks like there is nothing going beneath the superconductor, so both modes go around. So I just wanted to ask, why is it so, and why is it different?
Right. I think let's see whether so there are indeed kind of discussions that the edges between the superconductor and the quantum channels. Basically, you expect the Schusch and Zhang's paper. One of the papers described that this the edge state can be decomposed into the two Majorana state traveling with a different speed, right? So that's kind of one way. Now, I think that can be mapped back. I believe that can be just mapped back into in my languages. Basically, this Cross-Andreev edge states. Oh, no, sorry, the Andreev edge state, electron and hole is kind of the kind of converting each other. So I believe that's basically the same thing, right? The interesting part is the what if that you start kind of create the defects into those kind, or that try to localize that traveling the Majorana mode, right? In some sense, you can view that this finger with the edges is one of the efforts that I'm just trying to localize this the Majorana mode at the end. So using the very similar idea that if I just apply the integer quantum Hall effect, then in this end of the superconducting finger, I expect to see that there is a Majorana 0 mode is localized there, right? And then very similar with this the nanowire model. And in principle, we should be able to see that this tunneling, the signatures, zero bias in the tunneling the conductance. So that is one thing that we wish to just kind of also realize. We have some device actually is ready to go. I think it's not produced the data we want to see yet, but I think certainly that is another the indirect evidence showing that this can be just viewed as the localizing Majorana mode by just stopping this traveling Majorana mode.
Okay, thank you.
And so apologies for the speller turning Sasha Schneerman into Alexander Svatius. Last question. I saw Yuichi raise his hand. Yuichi, would you like to ask a question?
No, I have no question. Thank you.
Okay. Then thank you very much, Phillip.